So we were looking at the shortcuts for telling if an equation formed a line on the graph. So I want to quickly review that. There we've got Richmond. Is that going to form a line on the graph? Yes. It's got an exponent, but it's not on the variable. Is that one going to form a line on the graph? Yes, again, the root is an exponent, but it is not on the variable. Is that one going to form a line on the graph? Careful. Why not? Yeah, the variable is the exponent, is the power. Yep. So that one is out. How about that one? Will that form a line on the graph? No, because there's, again, powers on our variables other than one. Will that one form a line on the graph? Yes. That one's just fine. Will that one form a line on the graph? No, why not? Yeah, we're dividing by a variable, or there's a variable in the denominator of a fraction. Good. So we can look at these equations and we can tell rather quickly that whether they're going to be a line or not. So once we know that they're going to be a line, hopefully there's some shortcuts we can use for graphing them. So let's look at some fairly simple linear equations. Now I'm going to start out with the simplest linear equation I know, y equals x. We make a simple table. Now one thing, if we know it's going to be a line, yesterday we were making 4 or 5, sometimes more points in order to figure out what shape it is. But if we know it's going to be a line, we only need 2 or 3 points to be sure of where it is on the graph. 2 points is all we have to have. I always do a third point just to make sure they line up so I know that I didn't mess something up. So I'm just going to pick some values. If x is -2, what does y have to be? -2, y equals x, right? If x is 0, what's y have to be? 0. If x were +3, y would be 3. So I've got -2, -2 right there. 0, 0, that's my origin. 3, 3 right there. We're working now, looks like. Thanks. There's our line. Now, a couple things about our line. One, it goes through the origin, and it seems to angle corner to corner across our graph at like a 45-degree angle. That's the simplest linear equation we can have, y equals x. So some things we can do to complicate it. Just as we were talking before when we were looking at solving equations, we can do any of our basic operations to an equation. Add, subtract, multiply, divide. We can't do powers and roots because that makes it not linear anymore. So let's stick with those three, add, subtract, multiply, divide. If I add to the x, let's do y equals x plus 2. Let's see what that does. If I make a table, if x is -2, what's y have to be now? 0, because negative 2 plus 2 is 0. If x is 0, what's y? 2, and if x is 3, y would be 5. So we plot those. Negative 2, 0 is right there. 0, 2 is right there. 3, 5 is going to be up there. Well, first thing we notice is that line goes at the same angle across our graph. It's parallel to the first line. So we haven't changed its angle or how steep it is. All that is changed is it's moved up 2 units, right? So adding 2 to the x causes the line to move up 2 units. What do you think would happen if we subtracted? Like y equals x minus 3. What do you think that's going to do? Move it down 3. Let's check and make sure. So if we have x and y, if x is negative 2, what would y be? Negative 2 minus 3 would be, I heard it in Richmond there, negative 5. If x is 0, y would be negative 3. And if x were 3, y would be 0. So we've got negative 2, negative 5, 0, negative 3, 3, 0. Once again, pretend my lines are straight. We see that that goes at the same angle across the graph. All that is changed is instead of going to the origin, it is moved down 3 spaces. So subtracting 3 from the x moves it down 3. Later on in the course, we'll see that what's actually happening there is we are actually adding 3 to the y. Y plus 3 equals x is equivalent to y equals x minus 3. That'll give us this same table. So when you add 3 to the y, it moves it side to side instead of up and down. Notice we could have equivalently said, rather than moving down 3, that we moved over 3 from the origin. So we've added to x to see that it moves the line up. We've subtracted from x to see that it moves the line down. What if I multiply x by something? What if I do y equals 2 times x? Well, let's look at our table, x and y. If x is negative 2, what would y have to be? Negative 4. If x is 0, y would have to be 0. And if x is positive 3, y would have to be 6. So we've got negative 2, negative 4 is going to be somewhere in here. 0, 0, and 3, 6. Well, we see a couple of things here. One thing that we see is that we're back going through the origin again. We're back going through the center of the graph. The second thing we see is our angle is much steeper. Multiplying by 2 made that line steeper. So with that said, what do you think is going to happen if we divide? Like y equals x divided by 3. What do you think that's going to do to it? Will be flatter or shallower. Rather than saying x divided by 3, I'm going to write it like this. Y equals 1/3 times x. We know from our fractions that dividing is the same as multiplying by the reciprocal. So rather than dividing by 3, we're going to multiply by 1/3. It'll have the same effect. Now I'm going to, instead of using negative 2 for x, I'm going to use negative 3 to make it easier. If x is negative 3, y is going to have to be negative 1. Perfect. If x is 0, y would be 0. And if x is 3, y would be 1. We're at negative 3, negative 1, 0, 0, and positive 3, 1. Gives us that line right there. Any questions? So far, however, all of our lines as we move left to right across our graph have gone up. Some steeper and some shallower, but they've all gone up. What do you think we would have to do to make one go down? Let's try y equals negative 2 times x. If x is negative 2, what's y have to be? Positive 4. If x is 0, y would be 0. If x is positive 3, y would be negative 6. We've got negative 2, positive 4, 0, 0, and 3, negative 6. We see that that line indeed does go down instead of going up. That is referred to as a decreasing line. These other ones are referred to as increasing lines. At some point coming up here, we'll talk about inverse related and direct related. Direct related is increasing. One variable gets bigger, the other one also gets bigger. Inversely related is a decreasing. One variable gets larger, the other one gets smaller. Now, as we saw with these, all of these lines went through the origin here at the center of our graph, unless there was something subtracted or added to our variables. Multiplying just changed the angle, not where it goes through the center of the graph. There's only really two things that can happen to our line. It can be shifted up or down, and we can change the angle. And when we look at the equation, what's being done to our x variable tells us what happens with each of those two aspects. The minus 3, we subtracted 3 from our variable. That's telling us that from the origin, instead of going through the origin, we go down 3, that line goes through that point right there. The 2 tells us that it's steeper than normal. So instead of going at a 45-degree angle across our graph, it's going to go something like that across our graph. So this value here that was added or subtracted, that's our starting point, or initial point, is called the y-intercept. It's called that because here's the y-axis. If you look at the y-axis, that's where it intercepts or crosses the y-axis, is at negative 3. This number that multiplies the x, that tells us how steep it is referred to as a slope. Now we're going to talk more about slope over the coming hours, but a slope is always a ratio. It is a rise over a run. Now you might be looking at that too thinking, well, that's not a ratio. Well, any whole number can be turned into a fraction or a ratio by simply putting it over 1, 2 over 1. So that is saying is from our starting point, the negative 3 here, we rise to, we go up to, and we run or go over 1. So that's our second point on the line. And the line goes through those 2 points. Well, let's talk a little bit more about those intercepts. So let's say we have a line that looks something like this. We've mentioned a y-intercept. And a y-intercept is very important in our graphing. As we saw, it's our starting point for a line. The y-intercept, of course, is where we cross the y-axis. So if we look at that y-axis, what value does it cross, that line cross the y-axis? At 3. So our y-intercept here is y equals 3. We didn't discuss it previously, but there's also something called an x-intercept. And just as you might suspect, that's where the line crosses the x-axis. So for this line, what value does it cross the x-axis at? 5, right there, x equals 5. So our y-intercept is y equals 3, the x-intercept is x equals 5. But remember, we're dealing with a two-dimensional graph. What is the actual coordinate of this y-intercept? What's 0, 3? Very good. The x-coordinate is 0 because we're on that y-axis. We have not gone side to side at all. So we are at 0 in the x direction. So that x-coordinate, the x-coordinate of our y-intercept will always be 0. What is the ordered pair or the coordinate for our x-intercept here? 5, 0. Very good. Because it is on the x-axis, we have not moved up or down in the y direction at all. So the y coordinate of our x-intercept is always 0. So what that does is it provides for us a strategy for graphing equations if we know they're going to be aligned. If I want to graph this equation, now notice it looks very different than those simple ones we were graphing earlier. But I can graph it by using those intercepts. If I want to find the y-intercept, I know that the y-intercept always occurs when x equals 0. So I can find that y-intercept by replacing x with 0. So it's 3 times 0 minus 2 times y, or 2y equals 6. Now we do a little bit of combining. What is 3 times 0? 0, right? 3 times 0 is 0. So that really essentially is gone. What we have here is simply negative 2y equals 6. What do we do from there? We divide by the negative 2. Good. We divide by negative 2 to get y equals negative 3. Now remember, up above, we already said that x was 0. That's why I put 0 in there. So the coordinate we just created was x is 0, y is -3. So x is 0, y is -3 is right there. That's my y-intercept. To do my x-intercept, what do I know is always true at my x-intercept? Y equals 0. Very good. So if y equals 0, my equation is going to become 3x minus 2 times 0 equals 6. So from here we do our order of operations. What's 2 times 0? 0. Okay. So that's 0. So basically it cancels out. We don't need it anymore. 3x minus 0 is just 3x equals 6. What do we do from there? Divide by 3. So x equals 2. And if you recall, we set up above that y equals 0. So it gives us the ordered pair, x is 2 when y is 0. So the coordinate 2, 0 is right there. That is enough information to graph our line right there. In your notes, I want you to try to do this one for me. Find the x-intercept and y-intercept for that equation and graph the line. I'll give you a minute or so, and then let's see how you've done so far. So how do we find the y-intercept? Let x equals 0. So that equation will become the whole thing for now. Perfect. 5 times 0 plus y equals 10. And of course, that reduces. 5 times 0 is 0, just y equals 10. So the y-intercept, probably should put my lines closer together here. There we go. The y-intercept is at 10. 0, 10 is my y-intercept. How do I find my x-intercept? We let y equal 0. So when I substitute it in, what does it look like? 5x plus 0 equals 10. And of course, this 0 kind of disappears. And to solve it, I do what? Divide by 5 to get x equals 2. So that corresponds to the coordinate x 2, 0. Perfect. X is 2, y is 0. That's right there. There's our line. What do you think so far? Is that a linear equation? X equals 4. Sure it is. Yeah, there's no powers on our variable. We're not dividing by the variable. The variable isn't a power. That should be a line. the x-intercept. At the x-intercept, y equals 0, correct? If I put 0 in there for y, what do I get? Trick question, right? Y isn't in there, so y can be whatever I want to. X still equals 4, doesn't it? So the y-intercept to this is x equals 4, or 4 comma 0. That's the, did I say y? That's the x-intercept is x equals 4, so 4 for x, 0 for y, 4, 0. So that x-intercept is right here. The y-intercept. What values do we change? How do we find the y-intercept? We put 0 in for x. If I put 0 in here for x, can that ever be true? No, x can't be 0. What that's telling me, if x cannot be 0, x can never be 0 in that equation, there is no y-intercept. Well, if two lines never intersect when they're in a flat surface like this, what's the word we use to describe two lines that never intersect? Parallel. So the only way that line can never intersect the y-intercept, in other words, the y-axis, the only way that line can have no y-intercept is if it is parallel to the y-axis. In other words, it is a vertical line. Is that a linear equation? Why not, right? There's no powers on the variables. We're not dividing by any variables. That should work. If I want to find the y-intercept, how do we find the y-intercept? Now you let x equal 0. Well, there's no x in there, so the y-intercept is y equals 3, giving us the coordinate x is 0, y is 3. It doesn't matter what x is because x is not in the equation. Y still equals 3. So 0, 3 is our y-intercept. How do we find the x-intercept? You put 0 in for y. Is it possible for y to equal 0 here? No, it is not possible. Y can't equal 0. So that means there is no x-intercept. The only way that we can have no x-intercept or never cross the x-axis is if it's a horizontal line. It is parallel to the x-axis. Now, if you think about it, it makes sense. Y equals 3. Well, what's the y-coordinate of that? 3, right? What's the y-coordinate of that? 3. Every point on that line, y equals 3. Same up here for this vertical line. X equals 4 is the equation. The x-coordinate of that point is 4. And that point also 4, and that one, of course, also 4. Every point on that line has an x-coordinate of 4. We're saying we don't care what the y-coordinate is as long as the x-coordinate is 4. What if we're looking for points outside of those intercepts, where we're not zeroed in on x equals 0 or y equals 0? What if we have the equation 3x plus 4y equals 24, and I want to find a coordinate with y equals, let's see here, y equals 5. Really doesn't matter. We can work with fractions, right? How would I go about doing that? Perfect. I replace y with 5. So it's going to become what? Yeah, 3x plus 4 times 5 instead of 4 times y equals 24. Then, of course, we do combine. So this becomes 3x, as you said, plus 20 equals 24. What do we do next? Subtract 20. Gives us 3x equals 4. And then divide by 3 to get x is 4/3. Now you could leave it as 4/3 or 1 1/3. It doesn't matter to me. My math lab may prefer the improper fraction. But I haven't answered the question yet. What do I still have to do? Find the ordered pair. What's it going to be? 4/3, comma 5. If you had 1 1/3, comma 5, that's acceptable as well. So in your notes, find the coordinate for x equals 6. I'll give you a minute to work on that. So how do we start this one out? We put 6 in for x. Good. So there you go. 5 times 6 minus 3y equals 30. Perfect. What's next? Five times 6 becomes 30. Yep, 30 minus 3y equals 30. And then subtract 30 to get negative 3y equals 0. And then divide by negative 3, y equals 0. So the answer to the question is 6, comma 0. Very good. Try this one in your notes. Is the coordinate, the ordered pair 5, comma 3, a solution to the equation 4y minus 2 equals 2x plus 3? I'll give you about half a minute or so, and then we'll go over that. So where do we start? Okay, so this becomes 4 times 3 minus 1. Okay, and this becomes 2 times 5 plus 3. Now, technically, we should have a question mark here instead of an equal sign because we're not sure that it equals yet. What should we do next? 4 times 3 is 12. Minus 1 is 11. Okay, so the left side equals 11. And then 2 times 5 is plus 3 is 13. Is that equal? No, it is not equal. So no, it is not a solution because it doesn't give us the same value on both sides of that equation. The other concept we talked about at the beginning here as we were graphing these lines, we brought up the word slope. And we said slope describes how steep a line is, how steep or shallow it is. That is what angle it goes across the graph. And we'd even mentioned a formula, slope equals rise over run. Looking on a graph, sometimes it's relatively easy to figure out the slope of a line. If it goes through nice, neat little points like this, we have to find 2 points on the graph that we can identify its coordinate. We have those 2 right there. In this case, of course, a little review. Looking at that line, what's the y-intercept? 0 what? Careful. There you go. Y-intercept 0, negative 3. The x-intercept is 4, 0. Perfect. Our slope is rise over run. Run always goes left to right, just like reading a book. Rise, of course, can be up or down. If it's up, it's positive. Down would be negative. So as we move left to right, this is our first point. To get to the second point, we have to rise up 1, 2, 3. So that's up, so it's plus 3. And we have to run how far? 1, 2, 3, 4. So that is a rise of 3, positive 3 over a run of 4. That's a slope of 3/4. So for this line, a little bit of review. Y-intercept is what point? 0, 5. Good. X-intercept? 2, 0. Perfect. We have our 2 points. Those intercepts happen to be our 2 points. Our slope is found between those 2 points. As we go left to right, of course, this is our first point. Are we going up or down from there? Down. So it's going to be negative. How far? How many spots? 1, 2, 3, 4, 5. Good. Negative 5. And we're going to run how far? 1, 2. So it's negative 5 over 2. That's our slope. Okay, that is a great observation. And yes, it is true if you know the y-intercept and the x-intercept. You can take that y-coordinate of the y-intercept and the x-coordinate of the x-intercept, and it will be the opposite of the y-intercept over the x-intercept. That is always true. We'll come back to something similar to that in a little bit that is a little bit simpler way of going about it rather than finding the x and y-intercept. It helps us get it straight from an equation. For this line, we don't see the x-intercept, but we do still see the y-intercept. What is our y-intercept here? 0, 6, yes. Since we can't see the x-intercept, it's not on our graph, we have to have another point somewhere in order to find our slope. So let's say our point here is at 5, 8. So to get over to it, obviously we had to go from 0 to 5. We're running 5. How far would we have to go up to get to that? From 6 to 8 would be up 2. Very good. We can always think of there as being this like invisible triangle that contains a rise and run. Of course, it's a right triangle. And exactly, we would have to go up 2. That's a slope of a positive 2, and we would run 1, 2, 3, 4, 5. So it's a positive 2/5 slope, or just a 2/5 slope. Now your observation, that ratio of the y over x, the opposite of the y over the x, we can use that now to find our x-intercept. What's our x-intercept going to be? Perfect. Yeah, negative 6 times 5 is negative 30. We divide by the 2 gives us negative 15. X is negative 15. So that is our x-intercept, is at negative 15, comma 0. Sometimes we have equations where we have lines where the y and x-intercepts might not be real clear. This point here might be 3, comma 4, and we might have a point over here that's 8, comma 7. We can still find our rise and run from those points. Again, we think of it as being that little kind of imaginary right triangle there. Which coordinate is going to tell us how far we have to go up here. X coordinate or Y coordinate? You got it. This is the y-axis here. The y-axis goes up and down. It's the y coordinate. What is the difference between our y coordinates? 3. That's going up 3. So then to find our run, that comes from the x coordinate. Very good. To get from 3 to 8, we would have to run 5. So that gives us a slope of 3 over 5. Positive 3, rise of 3 over a run of 5. With what we just did there, we can see that we didn't even necessarily need the graph for that. We could have just had those two coordinates. 3, 4, and 8, 7. And we could have found, knowing that the rise is the change in the y coordinates. 7 minus 4 equals 3. And the run is the change in the x coordinates. 8 minus 3 equals 5, giving us that slope of 3 over 5, or 3/5. So we have a formula describing the slope. The symbol that we use for slope in algebra is the letter M, and it is the change in the y over the change in x. This little symbol here, the little triangle, is the Greek letter delta. It's a capital delta. Small delta looks like a musical note, and that means change in. So delta y is the change in the y value over the change in the x value. A simpler way of expressing that looks like this. The change in the y value is simply the second y value minus the first y value. The change in the x value is the second x value minus the first x value. Yes, for my test, you can use your notes. So to find the slope between, I'll say the slope for a line going through -3, 5, and 6, -7. So our formula here, slope is equal to y2 minus y1 over x2 minus x1. The simplest way for me to do these is I label my points, point 1 and point 2. So now I look at y2 means the second coordinate, coordinate 2, second point I should say, the y coordinate of that point, which is -7. Minus y1 is 0.1, the y coordinate, which is 5. You'll notice there that the negatives are going to come into play there. What is -7 minus 5? -12. Good. For the x coordinates, x2 means you have 0.2, the x coordinate, which is 6 minus x1 means you go to point 1. The x coordinate is -3. What is 6 minus a -3? 9. Now we have -12 over 9. Both of those can be divided by 3. Gives me a -4 over 3. Now, because that is a slope, it's a ratio, we would never reduce that to a -1 1/3. We never reduce a slope to a mixed number. It always stays as an improper fraction. Because a slope is a ratio, it's not an amount, it's a comparison between a rise and a run. So -4 means that from wherever it starts, it goes down 4, and then the +3 run means it goes over 3. So that's the shape the line is going to be on our graph, something like that. So in your notes, find the slope of the line that goes through the points, 5, 2, and 13, 8. So what's going to go on the top for, how do we find our rise? 8 minus 2, good. Y2 minus Y1, that's going to give us 6. How do we find our run? 13 minus 5, good. X2 minus X1, and that gives us be brave. 13 minus 5 is 8, good. And that reduces, both divide by 2 to give us 3/4. So a rise of 3 for a run of 4 is our slope. We talked a little bit about data graphs, and many of our graphs actually will represent real data. So let's graph hours spent walking and distance traveled. We're going to go with blocks here. Oops, this should have been 40, not 30. Yeah, we're going to make this a little more interesting. Just because I don't have a grid here, I'm going to put in these little indicator lines for you. Now here we're looking at, when we're dealing with real life data, often the axes on our graph are not just one unit per marking on the graph. You can see on bottom here, each marking is just 1 hour, but going up the side, each marking is how much? 10 blocks. Good. What's the slope of this line? Well, there's a lot of ways we could approach it. One way is from what we just learned, we can just pick any 2 points on there. What's the coordinate of this first point here? There we go, I heard it, 420. What's the coordinate of this point? 840, perfect. So to find our slope, it is y2 minus y1, 40 minus 20, over x2 minus x1, 8 minus 4. 40 minus 20 is 20. 8 minus 4 is 4. What's the units on that 20? Blocks. What's the units on the 4? Hours. Now that reduces. 20 divided by 4 would be 5 blocks in 1 hour. Notice how I wrote that, 5 blocks per hour. That looks an awful lot like a speed or a rate. It is technically 5 over 1 blocks per hour, or 5 blocks over 1 hour. We hide the 1, kind of the fraction that goes into the unit, so we kind of hide the appearance of the fraction. But that's a speed. In many cases in real life, that slope is a rate of change. A rate or a rate of change. Now this one, since we're walking, the speed was kind of contrived. Blocks per hour is not a common unit. We'd be more familiar with miles per hour. But we might have something like this in a medical application. Again, this being labeled hours. And the volume of fluid in an IV bag, we'll label this in milliliters. Oops. I'll try to draw my line straight, maybe. There, let's do that. So now looking at this, what is the infusion rate? Well, the infusion rate is just the rate of change, or the slope. We start out, again, we can just pick 2 points. We've got 3,000 here. That is the point 0, 3,000. Going to here, that is the point 4, what? 1,500. Very good. So our slope, m, if I call this point 1 and point 2, we 1,500 minus 3,000 over 4 minus 0. 1,500 minus 3,000 is negative 1,500. 4 minus 0 is 4. We can divide that out. It actually becomes 375. What's the units on this top number? Milliliters per, what was the units on the bottom number? per hour. So that rate of change, that slope is 375 milliliters. Technically it's per 1 hour, but we usually exclude the 1. That's our rate of change. That slope is the rate of change. That's the flow rate here. Now technically it's a negative 375 because it was reducing the volume. When you deal with flow rates, there's 2 flow rates. There's the flow rate coming out of the IV bag, which is what we showed here. It's leaving the IV bag at 375 milliliters per hour. That's why it's negative, because the volume's going down. And then there's the flow rate entering the body, which is the opposite. It's the same number, but it's positive instead of negative. So now our next step for all this would be to put it together. We've looked at graphing these equations from intercepts. We would want to now look at graphing these equations using the slope as part of that graph. When we look at this graph here, remember y-intercept is going to be where x equals 0. Well, it's pretty easy to find that out of here. If I put 0 in for x, y equals 2/3 times 0 minus 5. Well, that just crosses off y equals negative 5. We had mentioned back up towards the beginning of class today, this number here that's added or subtracted is the y-intercept. So from the origin, we go down 1, 2, 3, 4, 5. That's our y-intercept. That's where this line starts. The slope being a rise over run, there's 2 ways it can be thought of. It can be, as we saw it, units of rise, units of change in the y over the units of change in the x, or it can be thought of as the rise per 1 unit of run. So up here, go up a ways. When we found this slope here of 3/4, we can think of that as being from a starting point going up 1, 2, 3 units, then over 4. Or we could think of it as for every 1 unit over, we're going up 3/4. Well, down here, to go over 1 unit means you would increase x by 1, correct? Going over 1 is an increase of 1 in the x value. Let's just pick a value for x. We already picked one here as x equals 0, y equals negative 5. They gave us 0 equals negative 5. So let's go over 1 unit. So if x equals 1, what's y going to be? Y will equal to 2/3 times 1 plus 5. 2/3 times 1 is 2/3. Plus 5 is 5 2/3. Y equals 5 2/3. Giving us the coordinate. Sorry, minus 5. That should be not 5 2/3, but negative 4 1/3, right? 2/3 minus 5. So that gives us the coordinate here of 1, negative 4 1/3, right there. So that point is x equals 1, negative 4 1/3. So when we went over 1 unit, how far did we go up? From negative 5 up to negative 4 1/3, we went up 2/3. So that number multiplying the x, as we pointed out at the beginning of class, is the slope. So a shortcut for graphing this equation, if it's in this form here, it's called y-intercept form. The shortcut for graphing it is to start at the y-intercept at the negative 5. So from the origin, we go down 1, 2, 3, 4, 5, right there. And then the slope of 2/3. Well, for me, it's easier, rather than going over 1 and up 2/3, it's easier to do like we did before, up 2 over 3. And there's the second point on my line. That is where we will pick up next Monday, is with slope-intercept graphing. For now, you have homework 3C that pertains to this material. Remember, homework 3C, actually all the homework 3s. Homework 3, A, B, and C will be due for Monday. And of course, quiz 3 is also due for Monday as well. Anybody have any questions before we let you out for the day? Okay, you guys have a great day, and we'll see you on Monday.